right, so this particular slideshow is going to cover creating solutions by dilution. I'm also going to review how to make a solution from a solid, usually an ionic solid that can dissolve in water. That was covered in learning target number 3. And we're going to review that again because making solutions is a really important skill that you need to have for chemistry. And then we're going to learn the dilution equation to prepare a dilute solution from a concentrated solution. I'm filming this on Earth Day, and you may have heard in the past the phrase, the solution to pollution is dilution. We're going to put an equation to that today. Again, this should already be written in your notes somewhere. In learning target number 3, we learned the equation C equals N over V, where C is concentration in moles per liter. Notice here that I have the American units for this, moles divided by liters, but you'll see this be dm to the -3 in IB land. N is moles, V is volume, and we always need to make sure when we're using this equation that the volume is going to be in liters. So let's just do another quick review using this equation. So let's say we would like to create 150 milliliters of a 0.1 mole per liter solution of sodium nitrate. How would I do this? Well, I'm going to analyze what I've got here. I know that I have a volume of 150 milliliters. I'm going to immediately change that to liters by moving the decimal 3 places over to the left. I've got a concentration, and I don't know how many moles I've got. So here's my concentration equation. I'm going to rearrange that for moles, and then I'm going to fill in the information I've got. 0.150, and that's going to give me my number of moles. So this is going to turn into 0.0150 moles of sodium nitrate. So then what I'm going to do is I'm going to remember my molar mass of sodium nitrate. Sodium nitrate has a formula of NaNO3, making sure I'm looking at my oxidation states and that they cancel each other out. So I've got 1 sodium that has a molar mass of 23. I've got 1 nitrogen that has the molar mass of 14, and I've got 3 oxygens that have the molar mass of 16. So getting my molar mass here, I'm going to have 85 grams per mole. So I can multiply this by 85 grams in 1 mole. And I'm going to reach over and grab my calculator and say 0.0150 times 85. I need to dole out from my container 1.275, and actually since I've got 3 sig figs, or excuse me, I've got 1 sig fig here, I'm going to need to dole out 1 gram of sodium nitrate. And so to make this, I would take 150 milliliters of water, and I would stir into that 1 gram of NaNO3. And that's how I would make that solution of sodium nitrate. So why do we care so much about concentration? The more concentrated a solution is, the more particles it contains. The more particles a solution contains, the higher probability a collision between the particles are going to occur. The higher the probability of a collision, the faster a reaction will happen. So to show you this, I've got just a random particle generator. They're going to call this a gas, but you can pretend it's a liquid as well. And you notice that when I have this particular concentration of whatever solution I've got, there's some collisions that are occurring, but not so many of them. If I increase the number of particles, the more collisions I get. The more collisions I get, the faster the reaction is going to occur. It's incredibly important to know that the higher the concentration, the faster a reaction will happen. So this is why we care so much about the concentration of any reagents or products that we make in the chemistry lab. So how does this relate to acids and bases? Because eventually we're going to relate this all to acid and base reactions. Well, first and foremost, acids and bases are incredibly corrosive. They will hurt you if you get them in your eyes, nose, throat, or skin. The most important factor to consider for how corrosive an acid or base may be is the concentration of that acid and base. So when we buy hydrochloric acid, which we've used a couple of times in chemistry lab, for the teachers to use, we buy it with a concentration of 12 molar or 12 moles per cubic decimeter. And that is a concentration that is incredibly dangerous. If you spilled that on your pants would end up having a hole in them. Our stomach acid is also hydrochloric acid. Our stomach acid has a concentration of about only 1.16 moles per liter. Now, if you have acid reflux and you burp sometimes, you feel the acid in your throat and it kind of stings, yeah, it's still not the most pleasant thing to get on you, but it has a much lower concentration. Same substance, different concentration, different level of danger. This is a true story. I'm sorry I'm not in school to tell you this true story. I had a former student who went to Wazoo, and he was on work study, and he ended up getting a job in the chemistry lab. He was a good enough chemist when he left high school that he could actually make solutions for chemistry professors. Well, he had a little bit of an accident, was not wearing an acid apron one day and spilled 18 molar sulfuric acid onto his pants. And they ended up burning holes right in the front of the pant legs, big, huge holes. And so I think about it, jeans nowadays, you kind of pay for those holes in there, and you wonder, maybe that's how the holes get there instead of cutting them up. Anyways, that was a complete side note there. Let's talk now about dilutions. Dilute solution will have less particles per liter than a concentrated solution. So I've got an example of food coloring here, and this is 2 molar, 1 molar, 0.5 molar, and 0.25 molar. And what you notice here, as the concentration is halved, the number of molecules in that particular sample are halved as well. So if 2 molar solution had 120 di molecules, 1 molar solution will have 60, half a molar solution will have 30, and 0.25 molar will have 15 di molecules. And you can tell the difference by the change in color. There is a formula that helps you go from a concentrated solution to a dilute solution. And this is going to be one of your favorite formulas to use in chemistry, especially if you carry on and do an IA where you have to make your own solutions. In order to make a dilute solution from what we call a stock solution, or a solution with a higher concentration, we use the formula M1V1 equals M2V2. You will also see this as C1V1 equals C2V2. They're both the exact same thing, where M1 is the initial concentration, the concentration that you're given. V1 is how much of that initial concentration you need to use, so what volume. M2 is going to be the desired concentration, what you're going to, and V2 is the volume of solution needed. You use this equation to go from a concentrated solution to a dilute solution, because you really can't go from a dilute solution to a concentrated solution, because you would have to add more particles to it, and if it's a liquid, that's be really hard to do. So let's look at an example of how this equation works. So for example, I dilute 250 milliliters of a 0.10 mole per liter lithium acetate solution to a volume of 750 milliliters. What will the concentration of this solution be? So I'm going to look for the variables that I have in this problem. And make sure my pen is turned on. I'm going to call that V1 because that's the initial volume I'm going to start with. I'm going to have an M1, that's my initial concentration I'm going to start with. And the volume of 750 is going to be my V2. And what my new concentration will be my M2. Now, one really nice thing about this M1 V1 equals M2 V2 equation is that as long as the units for my volume match each other, I don't have to go back and change to liters. So I've got M1 V1 equals M2 V2. And notice my volumes are both in milliliters, so yay, they match. I don't have to change anything. So I'm going to have 0.10, 2 sig figs there, to 250, 2 sig figs there. And I want the concentration, so I might as well divide both sides by V2 here to get 750. And that will leave me with M2. And then I just solve it out. The 0.10 times the 250 divided by 750. And with 2 sig figs, I find my new concentration is going to be 0.033 moles per liter of lithium acetate. And I can get that formula directly from the periodic table and polyatomic table. So this is the first example of how to use that dilution equation. This next example here is a real life chemistry lab example, which is a technique that I perform almost always when I am preparing for you to do labs in class. So also think about this as a job opportunity. If you could do work study at college, you can get a better paying work study job. If you know a little bit about a chemistry lab, you can get a job as a lab technician. So you're able to do this. Maybe it'll help you later on in the job market. A class requires 500 milliliters, there's a volume, of 0.10 mole per liter HCl, there's a concentration, or a molarity, they're the same. How would I prepare this from a 12 molar stock solution of HCl? That'll be M1, this will be V1. So here comes my equation. M1 V1 equals M2 V2. And I'm not going to need to change the units here to liters because I'm looking for a volume and I might as well leave it in milliliters. So I'm going to have 0.1 mole per liter of the HCl. I'm going to have 500 milliliters here. And I'm going to divide that by the 12 because I want V2. So then solving that out, I'm going to have the 0.1 times the 500 divided by the 12. And I'll find out what volume of hydrochloric acid I need. And in this case, I only have one sig fig again, so it's going to be 4 milliliters. So in order to make this solution, I have a total of 500 milliliters. So I would add 4 milliliters of the 12 molar, and I would add that to 496 milliliters of water. Notice here that when I add those together, it equals 500 milliliters. So whatever volume I am adding to the water in order to make it dilute, I have to subtract that from the total volume that I have here, so that my total volume is going to be my required amount of 500. That will ensure that my concentration is correct. So also, safety note here, whenever you're making solutions, the rule is always add acids. So I would put 496 milliliters of water in first, and then I would slowly pour the 4 milliliters of 12 molar HCl, so I don't have a reaction and the acid splashes back up into my face. All right, you are going to find some practice problems on the assignment and Schoology that go along with this. If you have any questions, as always, do not hesitate to ask. Happy Earth Day again while it's raining. Have a good day.